Next example, example 2.7. This one has a little more substance to it. The partition function for a system is given by, and there's the full partition function, as this exponential e to the a cubed t to the 3 halves times the volume cubed. And a is just a constant term that I guess is determined in some theory that one has, whoever developed this partition function. Notice once you have the partition function, you can get just about anything that you want. And in this particular case, what's asked for is what's the average energy. That would be the average energy per particle in the system, and find the average pressure, and then ultimately the pressure of the system. So let's launch into part 8. We showed this in class, and it's also given in table 18.1 in your textbook. But the average energy is kb t squared partial of t with respect to the natural log of the partition function. Since we're given the partition function, then we just substitute this in here, and we have to calculate this partial derivative. Usually when you work these, it's best to go ahead and write this natural log out of a natural log of each term, but in this particular case, it's actually better to just realize that the natural log and the natural exponent are inverse functions of one another, and so this reduces the natural log of a natural exponent is just the argument of the or the power in the exponent. So it's a cubed t to the 3 halves b cubed. I can pull out terms that don't depend on t, partial derivative with respect to t, so a is a constant, so I can pull it outside. V is a constant with respect to partial differentiation with respect to t, so I can pull that one outside as well. And I'm left with just taking the partial derivative of t to the 3 halves, which of course is multiplied by the exponent and then reduce the exponent by 1. So this partial derivative is 3 halves t to the 1 half. The rest of the stuff just comes down. And so I get the average energy is 3 halves. I pull that up front. kb t squared is and t to the 1 half turns into t to the 5 halves. I've got my a cubed here and then the v cubed here. So the average energy is just that. Average pressure, just use the other formula that we developed in class. Remember, average pressure was kBT, partial v with respect to the natural log of z. And again, that's given in the table 18.1 in your book as well. Same story. Natural log. Just plug in our expression for what we're given as the partition function. Take the natural log of it. That just gives me the exponent. And the only difference is now we're taking the partial derivative with respect to v, treating t as a constant. And once I do that, then the a cubed can come outside. The t to the 3 halves can come outside and just becomes the partial with respect to v of v cubed. And the derivative of v cubed is just 3 times v squared. And then I just reordered it to get the average pressure. It's the average pressure per particle of the gas. If there's n particles of gas, then the gas pressure is n times that average pressure. And when I do that, multiply this by the number of particles, I get 3n kb a cubed t to the 5 halves v squared. And more often than not, you'd multiply and divide by Avogadro's number. Na times kb is just the ideal gas constant, and n over is just the number of moles of the gas. So the pressure, again I'm using small p for pressure, is 3 nRA cubed T to the 5 halves V squared. And that you would recognize as an equation of state, which I've abbreviated here as EOS, so equation of state. So oftentimes that volume one is used to obtain equations of state for a particular substance. Works well for dilute gases, but to some approximation in other contexts as well.